Hi everyone, welcome to Camp GD. I'm Michael, and in this video, I'll be showing you how a little bit of applied biochemistry can make your food not just taste sweeter, but actually be sweeter, without adding any sugar or any additional ingredient at all.
The trick relies on amylase, which is a naturally occurring enzyme that catalyzes the hydrolysis of starches into sugars. An enzyme is a protein that acts as a biological catalyst. A catalyst is a substance that increases the rate of a chemical reaction, in this case, the breakdown of starches into sugars, without undergoing any permanent change itself. It does this by reducing the activation energy necessary for the reaction to occur, which means that the reactions will occur at a faster rate. Then, hydrolysis is a category of reaction in which water breaks one or more chemical bonds, in this case, the bonds of the starches, therefore converting those starches into sugars. Amylase is naturally found in saliva, egg yolks, and certain fruits and vegetables, among other sources. And before the question crosses your mind, no, I'm not going to be suggesting that you spit in your food to make it sweeter. But knowing this, why does it matter? Well, we can manipulate amylase that's already present in foods to reduce their starchiness and increase their sugar content. How can we do this though? Well, we need to understand the reaction kinetics, or the physics of chemical reaction rates. For a simpler chemical reaction, we might be able to directly take the reaction rate law and the Arrhenius equation and analytically calculate the factors that affect reaction rate. But catalytic kinetics and enzymatic kinetics, even more so, are pretty complicated. So an empirical understanding is good enough. Looking at the graph, you can see that as temperature increases at first, the relative activity increases as well. This is because the kinetics of the reaction are becoming more favorable. However, as the temperature increases past a certain point, it begins to decrease as the protein structure that makes up amylase begins to degrade. After that point, it's no longer helpful since the amylase molecule itself is falling apart, and we want to instead maintain a temperature really between 50 and 60 degrees Celsius for optimal reaction performance. Knowing that, these are the lessons learned that we can take away. To make our cooking sweeter without adding any sugar, we must either increase the activity rate of pre-existing amylase by maintaining the optimal temperature zone of 50 to 60 degrees Celsius, or we can introduce amylase to starches earlier in the recipe, since that earlier exposure means that there will be a longer time span for those starches to be converted into sugars. Now, activity time. We can put what we learned into use. First, we'll be making banana muffins. Banana bread and banana muffins are always listed as a way to use up overripe bananas. But what if you want banana muffins and you only have underripe bananas? Well, that's what we'll be showing today. Next, roasted sweet potatoes. Despite sweet potatoes literally having sweet in their name, they're often glazed with even more sugar after cooking. This recipe will activate the potato's inherent amylase to produce sweet potatoes that are so sweet, anything further is just overkill.
First, we're going to make banana bread, or in this case, banana muffins, since I don't have a loaf pan, but I do have this muffin tin, and you can convert basically any quick bread recipe into muffins. The ingredients shown here are listed in the description of the video. Mash 2 bananas together along with 1 egg and then set aside for 30 minutes. This time it will allow the amylase in the egg yolk to convert much of the starch in the mashed bananas to sugars. In the meantime, combine the flour, salt, and baking soda in a bowl and whisk vigorously. After 30 minutes, mash the remaining egg and bananas together in a bowl. Now we can compare the two batches of mashed banana and egg. In addition to being darker due to oxidation, the first batch should be thinner and sweeter, since some of its starches have been converted to maltose by the amylase. Add the sugar, butter, and Greek yogurt to a bowl. If you have a scale, take note of the weight now. Beat together until light and fluffy, around 4 minutes. fold in the dry ingredients, stirring as little as possible while still combining everything. Divide the mixture in two, adding 1/2 to each batch of mashed banana and egg. Fold each bowl of batter until just combined, then add in chocolate and walnuts if desired. Fill each muffin tin with just under 1/2 cup of batter, and then bake at 350 Fahrenheit until domed and just beginning to brown, around 25 minutes. Keep track of which muffins used which batter. Now that we've baked the muffins, let's talk about it a little bit. Having taken a bite out of both of them, I can say totally honestly that they are both absolutely delicious, and I wouldn't turn down either one. But knowing that there is a difference between the two, it was certainly detectable. The one that I treated with amylase, it's noticeably sweeter and moister compared to the one that I didn't. And you might not be able to see it on this video, but when you do the experiment, you'll be able to feel that the one that you did not treat, that muffin, it has a lighter, springier crumb. It's a little bit drier too compared to the one that you treated with amylase. As you break down those starches to sugars, it makes the batter bake up a lot moister and a lot sweeter as well. And that is noticeable when you bake it. And what's great about this is that you didn't add any more sugar. So just by using that little bit of biochemistry, adding in the extra amylase from the egg yolk ahead of time, you're able to make a muffin that I think a lot of people would say is better without having to do anything but just take a little bit more time. Next, we'll be making roasted sweet potatoes. Although in the banana muffins we added amylase in the form of an egg yolk, in this case we'll be activating amylase that's already in these sweet potatoes. The ingredients, shown here, are again listed in the video description. Place half of the sweet potatoes in a pot, cover with water, and bring to 60 degrees Celsius, or 140 degrees Fahrenheit. Then let rest until room temperature. During this time, the amylase in the sweet potatoes will cook into overdrive, resulting in tender, naturally sweet potatoes. Keep the remaining sweet potatoes in a bowl at room temperature. Drain the amylase-activated potatoes and then toss each batch of potatoes with 2 teaspoons olive oil and salt to taste. Divide a sheet pan in two and add each batch of sweet potatoes to one side. Roast in a 400-degree oven until the bottom side is browned, around 30 minutes. Once that happens, carefully flip and roast again until both sides are browned, around 20 minutes more. Now that we've roasted off these sweet potatoes, hopefully you'll be able to immediately tell which half of this tray has the sweet potatoes that got the warm water bath treatment to activate the amylase. I'm going to give it away now, but it is this side. Immediately looking at them, you can tell that they're a lot more deeply browned, a lot more deeply caramelized than the other half, right? That's because sugars brown at a lower temperature than starches. In addition, when you pick them up, you'll be able to feel that they're a lot more tender. Because we reduced the starch content of the sweet potato, that means they're going to be a lot more tender, a lot less stiff, and hold on to a lot more moisture. And then finally, when you taste them, not only are they going to taste sweeter, but they're going to have a lot more complex flavors as well. Developing the sugars at the beginning enables the creation of Maillard pathways and this nice brown, roasty, toasty flavors that you just don't get without those sugars present on the outside. So with a little bit of patience, a little bit of biochemistry, we get sweet potatoes that taste a lot better. Well, that wraps up this segment of Camp GD. One of the reasons I love cooking so much is that it gives me an opportunity to apply a lot of the concepts that I learned about in the classroom, and I think, will I ever actually use those in real life? And I do get to use them. I get to apply them in a really practical, everyday situation. What we cooked today, that alone brought in concepts such as activation energy, catalysis, reaction rates, and reaction laws. But beyond that, I could go on and on. about subjects such as the importance of pH in Maillard reactions in browning, or pH and pectin activation, or the importance of emulsions and how those work when we're cooking, or how different thermodynamic concepts and laws relate to different methods of cooking, whether you're broiling or boiling or baking or braising or searing or grilling or deep frying versus shallow frying. I think you can see I could go on and on and on, but there's only so much time that we have in one video. So I just wanted to say, I hope you enjoyed this lesson, I hope you learned something new, and at the very least, I hope you can enjoy the sweet taste of science in the dishes that we made today. Thanks.